Hey everybody, my name is Chris and I'm a tutor here at Chegg.com. I mostly do math and computer science, and in this video I would like to go over the fact that if a polynomial equation f of x equals 0 has real coefficients, and if the complex number a plus bi is a solution of this equation, then the complex conjugate a minus bi is also a solution. Okay, so let's go ahead and see why this is true. So first of all, if f of x equals 0 is a polynomial equation, that means f of x is a polynomial, which means we can write f of x as a sub n times x to the n plus a sub n minus 1 times x to the n minus 1 plus dot 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 plus a1 times x to the first power plus a0. So here we have f of x written as an nth degree polynomial, okay? And if we set f of x equal to 0 and solve, then we have this complex number a plus bi that's a solution. And what this fact here says is that if we know we have a plus bi as a solution, then a minus bi must also be a solution. So why is that true? Well, first let's review some notation about conjugates. So remember, we have a complex number z equals a plus bi. Then the conjugate is denoted z bar equals a minus bi. So you just change the sign on the imaginary part, okay? Now for any real number, I'll call it c, we have c bar equals c. In other words, the conjugate of a real number is just that number itself. The complex conjugate of a real number is just that real number. Because remember, to find the complex conjugate denoted with the bar, you just change the sign of the imaginary part. Well, if you'd have a real number, the imaginary part is 0, so there's nothing to change. So you just get the same number back. Okay, so keeping this in mind, let's go ahead and see why this might be true. So first of all, we have 0 equals f of z. So let me say z equals a plus bi. Oops, a plus bi. And then we want to show, usually abbreviated capital W, capital T, capital S, want to show that z bar equals a minus bi also satisfies the equation. And what equation is that? It's the f of x equals 0 equation. Okay, so we know that z equals a plus bi satisfies f of z equals 0. Okay, so let's go ahead and consider then 0 equals 0 bar, right? Because remember, for any real number c, we have c bar is the same thing as c. So 0 is the same thing as 0 bar. Well, if 0 is f of z, then 0 bar is f of z, whole thing bar like that, right? So we have this. But what is f of z in terms of the polynomial? Well, remember, f is given by this right here. So in terms of z, what we have is a sub n z to the n plus a sub n minus 1 z to the n minus 1 plus dot 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 plus a sub 1 times z plus a sub 0. And this whole thing has a bar over it. Okay. Now, one of the facts about complex conjugates is that the conjugate of a sum is equal to the sum of the conjugates. So what we have here is the conjugate of this whole thing here, which is a big long sum. So we can split that up into the sum of the conjugates. So in other words, that's the same thing as a sub n times z to the n, conjugate of that, plus a sub n minus 1 times z to the n minus 1, conjugate of that, plus dot dot dot, plus a sub 1 times z, oops, that's a z there, it's supposed to be a z, conjugate of that, plus a sub 0, conjugate of that. Now let's go ahead and simplify further. Now, just like the conjugate of a sum is the sum of the conjugates, it's also true that the conjugate of a product is the product of the conjugates. So here we have the conjugates, a bunch of conjugates of products. So here a sub n times z to the n, a sub n minus 1 times z to the n minus 1, a sub 1 times z, and so on. So here we can split these up as a sub n bar times z to the n bar plus a sub n minus 1 bar times z to the n minus 1 bar plus dot 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 plus a sub 1 bar times z bar plus a sub 0 bar. There's no z over here. Now, a couple more things left to do. First, remember that this polynomial equation has real coefficients. So a sub n is real, a sub n minus 1 is real, a sub n minus 2, not shown, is real, a sub 1 is real, a sub 0 is real. All of these a's are real numbers. And remember that the conjugate of a real number is just the real number itself. So we can actually drop all this bar notation on the a's, not on the z's, just on the a's. So we have a sub n, z to the n bar, plus a sub n minus 1, z to the n minus 1 bar, plus dot dot dot, plus a sub 1, z bar, plus a sub 0. Okay, so again, we can do that because all of these coefficients, a sub n minus 1, etc., those are all real numbers, and the conjugate, the complex conjugate of a real number is just that same real number. But again, we cannot do that with the z's because with these z's right here, these are actually complex numbers that are not purely real. Okay, so let's move on to the next page and continue. So just to recap what we have so far, we have 0 equals 0 bar equals f of z bar on the whole thing equals some other stuff in between, and we left off with a sub n z to the n bar plus a sub n minus 1 z to the n minus 1 bar plus dot 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 plus a sub 1 times z bar plus a sub 0. Now here we're going to use one more property that we've actually just used. So z to the n bar, let's come off to the side separately here. Z to the n bar, this is a conjugate of a product, right? Because z to the n, that just means z multiplied by itself n times. And we're taking the conjugate of all that. So here, we're multiplying z by itself n times. So this is really just the same thing as z bar times dot 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 times z bar n times. Because remember, the conjugate of a product is the same thing as the product of the conjugates, which is actually a fact that we already used when we went from this step to this step. Okay. So now we're just going to use it again. So then this can be rewritten as z bar raised to the nth power. Okay. So if we come back up here, then we have a sub n times z bar to the nth power. And then we can do the exact same thing with the z to the n minus 1 bar over that. That's going to be z bar to the, oops, let's fix that, z bar to the n minus 1 plus dot 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 plus a1, z bar is still just z bar, and then plus a0. So what is this? If we wrote out some more terms, it might be a little more clear, but from here what we can see is, well, if we go back to our original polynomial, where in general we have f of x is x to the a sub n x to the n. Let's maybe use a different color here. Here's f of x. We have x to the n minus 1, dot dot dot, and then just plain old x. And in between we have x to the n minus 2, x to the n minus 3, and so on and so forth. But then going back here, what do we see here? Z bar to the n minus 1. If we wrote out the next term, it would be a sub n minus 2 z bar to the n minus 2. And here we have plain old z bar. So actually what we've written down here is exactly f of z bar. Okay. So right here we have our z bar, and that's what's being raised to the n right here. It's being raised to the n minus 1 here. It's being raised to the n minus 2 in the next term, and so on and so forth. So this entire thing is actually f of z bar. So let's rewrite that. Easier to read. And why is that significant? Well, because remember, this whole thing at the very beginning was equal to 0. So what we've just seen then is that, so we conclude, or so we see, shorter words, so we see that 0 equals f of z bar. Period. So z bar equals a minus bi is also a solution. Let's make that a little nicer. Is also a solution. Okay, so hopefully this helps you understand why, if we have a complex number that's a root of a polynomial equation with real coefficients, then the complex conjugate also must be a root. So this really comes down to just knowing that the complex conjugate of a real number is again a real number, that same real number, and just knowing that the conjugate of a sum is the sum of the conjugates. That's what we used from this step to this step. And also knowing that the conjugate of a product is the product of the conjugates. That's what we use from this step to this step here. Okay, and that's pretty much that. I hope that you found this video helpful, and thank you for watching.